Standing by for Sky Green. Sky Green is started. Touchdown confirmed. Proceed.
What a fantastic demonstration of what our nation and our agency can do. I could only think of the words of Teddy Roosevelt as I was sitting there. It is far better to dare mighty things even though we might fail, than to stay in the twilight that knows neither victory nor defeat. And the team brought us victory today.
Today, right now, the wheels of curiosity have begun to blaze the trail for human footprints on Mars. This is an amazing achievement.
Well, today on Mars, history was made on Earth. The successful landing of Curiosity marks what is really an unprecedented technological tour. It will stand as an American point of pride far into the future.
We've got a long mission ahead of us, and doesn't matter, and we believe this rover and possibly just monumental stories to accomplish.
Within 2 months, team found ancient riverbed, evidence of flowing water. We have found a habitable environment that is so benign and supportive of life that probably if this river was drowned and you had been on the planet, you would have been able to drink it.
Never gets
Yeah, so that's the landing. You know, you're kind of stuck because Mars is about 15 minutes away by speed of light. So there's nothing you can do. So all those people that were there looking nervous while it was landing, they weren't flying anything. They were just watching their screen as data was coming in 15 minutes after everything actually happened. That's just the nature of landing something on Mars. So everything they had worked for years to program Curiosity to fly itself down the table. And we were all sort of helpless that night. And it was all kind of through computer screens. You know, it's amazing that as emotional as that night was, and it was very emotional. The thing that is even more experience for me was the launch. Because you're there for your chest. I should do that. Very realistic. Your chest is thumping with with the rocket's vibration, and you know that you just spent like 6 years building this really delicate, complex machine. Viscerally, you're like watching it blast off in this controlled explosion into space, and not only is it just terrifying, but you really get the sense that you're sending something away from Earth when you see a rocket launch in August. So go do that. really get around it through many natural processes other than the most effective one on Earth is transporting speed. Like pebbles just rotating and colliding with one another in a speed that you can get, we measured all the angles of the rocks, calculated how rounded they were, the size of the rocks, compared them to different places on Earth, and it told us that we were actually driving through an ancient streetbed on Mars that probably had transported these pebbles for something like 10 to 15 miles. And the water was flowing somewhere between sort of ankle deep to hip deep. So it's a pretty good size stream, maybe even a river. For people who had seen for maybe a couple of decades, like me, rivers on pictures of Mars from orbit, you sort of know that these things exist. But when you're there and you're sitting around in pebbles and you think, man, we're driving right through an ancient streetbed, that just brings a whole new meaning to it. And so this is the first time that we really were able to find this evidence of that water flows on the surface of Mars through different strokes. We went to a place where that water may have collected into a lake, and our hypothesis was this flat area out here, how different it is now, the gravel's all gone. It's just a flat plane of rock that very much looks like it could be an ancient dry lake bed. And so we drilled into it. This is the first time we got out and drilled. Here we are drilling. The place is called we end up with a little dime-sized drill. And you can see a laser placed blasted down. So we're looking down with Curiosity from about 7 feet off the ground, firing our laser into a dime-sized drill and making a little arrow down the side. So it's a fantastic machine. And with that laser, we can now see if the composition of the rock changed as we drilled about 6.5 centimeters of 2 inches into the galaxy house. What's cool about this picture is that we drilled the rock and then we took this picture at night using our own LEDs, our own lights in the arm in the middle of the night. Now what's neat about that is that Mars is very stuffy. So any picture you take during the day always has an orange cast to it. Because the sunlight is very heavily filtered. It's like a very sleepy day on Earth. But if you wake up in the middle of the night and take a picture with your own light, actually color Mars is for the first time. So this is like a true color picture of Mars. And it's the bright orange. It's not as orange as it looks in the middle of the evening. And what's really cool is that the pattern that we drew is not orange, it's gray. And so the steel of Mars is oxidized, rusted, but you just drill a few inches into the rock and you can get more pristine material, which is a very good sign for one day finding evidence of life, because it means that the environment that's now changing Mars today hasn't penetrated that deep into the rock where things could have been living in. And we have destroyed all the evidence for this location. So what did we find? Here's a couple of pictures that show you the kind of data that we get. We drill into the rock and we put in the material into this laboratory, and the laboratory takes X-ray and it shines that X-ray through the rock pattern. It's called an X-ray diffractometer. Diffraction is a fancy scientific word for splitting light into different wavelengths, like creating a rainbow or shine light on a prism. We do that with X-rays, and the reason that you get these rainbow marks when you shine X-rays through rocks is that rocks are made of crystalline silicon. So every mineral is a kind of crystal that diffracts the X-rays in a different way. And so scientists can read these marks like fingerprints, the spacing of the arc, the intensity of the arc, and tell you exactly what mineral is doing. And if we find a clay mineral, like we did, this big rock down here is called silicate. It's a kind of basically clay. And so we found clay crystals in this hypothesized lake bed, which tells us that water was actually here and actually probably was a lake bed. The other experiment that we have, the other laboratory we have, is a gas chromatograph mass it's very common in this that you see on all the detective TV shows. The kind of thing that tells the what's the container. And the way we get the material out into the insert, you put the powder in the laboratory, and you bake it, and you bake it at about 100 degrees. And as you do that, the rock starts to degrade. And as the rock degrades, it's ramping up the temperature, different minerals decompose. And so it's time running left to right. And so a bunch of water first, because water and then as you heat it up more, carbon dioxide comes out, other things come out. And so you can sort of reconstruct what was in the rock based on how it degraded. And so these two pieces of information are corresponding together. And they work in synergy with each other. We can technically both parts to make and by blade. And the ring is much more. So we also found carbon, oxygen, sulfur, and found sources of chemistry because there was one example is there's different types of sulfur in here which have different chemical states. For those who are chemists, sulfur has oxidized sulfur minerals, and that's the kind of thing that microbes can do. So even at this very first time, we found water, we found key chemical ingredients in different biological sources. So we found a halogen, which was fantastic. So that took a lot of pressure off because we were able to tell supervisors that we were able to successfully accomplish the mission in the first year of our and then allowed us to the last 4 years we could add to that story knowing that we at least accomplished the basic elements. So the reason that's significant too is because we weren't planning to spend much time around what we were our bosses at headquarters. You know, we spent a couple weeks there, and then we'll go to Mountain very quickly after that. We spent about a year at this site because we discovered all this great stuff. So we kept saying, oh, just wait. But then we did finally pick up stakes. Remember, it turned out July 4th, 2013. We landed August 5th, 2012. So almost a year after we landed, we finally left this area after accomplishing all this and made a beeline for Mountain. And along the way, we found this spectacular rock formation. A bunch of sandstone that was all big slabs of sandstone. They were all tilting in one direction. And the direction they were tilting was facing the mountain itself. So as we were driving to the mountain, we came across more than one of these formations. And we studied it, and based on the evidence of finding the river floor and the lake, and studying the sand deposits and figuring out the sand particles were too big to have been transported by wind, must have been involved being transported by water. We concluded that this formation was a delta. So here's a little cartoon of what we think is happening. Water is flowing here from right to left, and you have water flowing downhill from the river. Then the water encounters the lake. And when you encounter the lake, that fast-moving river down. So all the sand is carrying, all the dirt is carrying with it to fall out. And so you end up with all these sand deposits right where the river meets below. And then as you go further into the lake, down on a silt begins to fall out. And you get these very fine layers of sand to the bottom. That's much stuff. Yeah, that's over here. So here's where you get your pebbles, here's where you get your sand, here's where you get your mud. So we found some pebbles, we found a little bit closer to the mountain, we found some tilted bits of sand. Then of course, our hypothesis was get close to the mountain, more lake, not the lake that we found out on the plane. annually as lakes replaced by streams, and then Arctic spots. So when you get a mountain where there was supposed to be a bunch of lakes. So here's our idea, is that Yellowstone area will form, and then that's where Mars was wet, and there was maybe precipitation, or at least groundwater. Groundwater flows through all the cracks in the rock, and they make a lot of clouds, and formed lakes that filled up the crater. And the lakes maybe never were that deep, but sediment continually brought in by the rivers, and that silt just settled out in these lakes, and slowly over many, many millions of years built up millimeter by millimeter, and the lake rose as the mud kept getting thicker. And then over time, so imagine, keep your eye maybe on this spot where imagine the river is right there. Over time, what happens is that the lake level was at one point here, and then it got higher and higher. And at some point, this stuff that was not really lake, it's just this dust filled it up even more. And then the climate of Mars changed in a way where was things brought near the crater, but now it's scouring out of the crater. And it's scouring it out in a way that sort of does this big hit into what is leaving the sand, this dusty stuff, and then the layer of lake sediment we're now studying. So these lakes have moved all the way across the lake was that's our story. And we're continually finding evidence to support it and making our case to the rest of society. Really, the usual process, lots of peer-reviewed papers, but so far we've learned these ideas by earth geologists, of course, they think we have a pretty good idea. So, we found driven about 18 map looking down. It's a plain land. This is the mountain with the layers of the mountain. Land here, we made all those discoveries right when we landed on Yellowknife Bay. Then we drove pretty fast, found the deltas kind of in here. We got to the edge of the mountain, about 2 years in position, and for the last 3 years, we've been slowly going up all the layers of the mountain, little by little. We're here right now, and we'd like to do this remaining segment before the mission ends. So hopefully we'll be able to do all that in the next 2 or 3 years, and once we get up to this layer, we will have studied all the layers on the mountain that appear to have formed through water. So far we've drilled about 15 holes. Here's 12 of them, and you can see there's kind of a variety. There's holes that the material is reddish when we drill it, so maybe the oxidation has penetrated into the rock. There's holes that most of them are pretty gray, and in those gray holes is where we tend to find the clay minerals and even organic molecules, very simple carbon-containing molecules that have survived because they haven't been oxidized and destroyed. And then we found a couple more red holes lately. I think the next few slides is a little bit more of a tour, just my favorite pictures. But just to give you another sense of the variety of things that we're seeing as we've been driving along the last few years. Here is a nice picture showing 3 pictures. There 3 billion years ago that have now turned into sand. And the third thing you see here is modern sand that's blowing around today. And so, when we're driving around, we have to sort of mentally ignore the modern stuff. It's not that interesting. We have to find the places where the lake deposits are exposed at the surface so we can go study them. And then we have to understand how this later stuff covered up some of the lake deposits and how it's related in timing. This is one of my favorite pictures. These are the Murray Buttes. These are several stories high, big buttes that we drove through. It's like you're driving through Utah or somewhere. Bugs Bunny and Roadrunner country. And you're driving through here. These are those lake deposits. And again, the sandstone is above them. And the reason you get these buttes, whether you're talking about New Mexico, Utah, sandstone is a little bit more resistant to erosion. These layers used to connect at one point. Eroded away, so you get these little towers. But eventually, another billion years, these will be gone too, leaving these lake deposits exposed. Here's the thing we saw at the beginning, the selfie. What's neat about this is we studied some of these modern sand dunes. It was actually the first time we've ever seen modern sand blowing around on Mars. The other rovers have seen ancient dune fields, but we actually were able to drive into dune fields and watch them actually moving, which is really cool too. Even though it has really nothing to do with life and our main goals of the mission, we're on Mars, you got to study it. And so we did some playing around, we dug some trenches, we watched sand avalanche, we watched sand blow, and one of the things we discovered was that, not surprisingly, there's a lot of similarities to sand dunes on Earth. The dunes have similar shapes because the physics is roughly the same, even if you have a thinner atmosphere and a little less gravity. But one thing that you do not find on Earth are these ripples. You find these small ripples, you can see those here. You go to Death Valley, you'll see dunes covered by these small ripples that are maybe a few inches apart. What you won't find are this other set of ripples that are about 3 feet apart. And what it turns out that those only form in the thin atmosphere of Mars. The totally different physics comes into play with the thin atmosphere in this case. And so you really are on Mars when you see those, which is kind of neat. This is just showing you some results from our weather station. What's plotted here, this is temperature in Celsius and Fahrenheit. I can't really read it, but I think this is minus 120 over here, and something 100 Fahrenheit over here. So this is Los Angeles over 2 years. And Los Angeles is nice and warm, and actually doesn't vary a whole lot from day to night. And this is Mars, to give you an idea of what the rover has to put up with every day. So Mars varies from summer to winter, like this, but the day-night differences are even bigger than the summer-winter differences. So every single day, now for 2,000 days on Mars, and 5,000 days for Opportunity, the other rover, you have these very sensitive electronics, moving parts, all this kind of stuff that has to survive these 100-degree plus temperature changes from day to night. There's, you leave your laptop out overnight in LA and it wouldn't survive the next morning. So it's yet another way that the engineers just have to really do some amazing work to make these machines last in this really horrible, extreme environment on Mars. We found a meteor. We actually are not the first rover to find these. It's not uncommon actually to drive across Mars and find meteors. And this is a big chunk of iron. We can shoot it with our laser, and we determined that it actually was an iron-nickel meteorite, which similar to iron meteorites you find on Earth. So that's kind of neat. Here's a picture of a rock slab. This is about 1 inch here, where we see all those thin layers that are similar to what you'd find in the lake bed that we think are indicative of a lake, ancient lake bed. But within this particular slab, there are all these little pimples on it. And when we look close at those little bumps, they have these interesting shapes. And those shapes are very similar to what you'd find if you dug below an ancient lake on Earth, or even a current lake on Earth, where gypsum or other salts are crystallizing in the mud below the lake. And so we found these little swallowtail shapes that are very diagnostic of gypsum crystals, which is a kind of salt that forms in lake beds as they dry up. And these crystals were forming in the sediment. So yet another circumstantial piece of evidence that we are actually studying ancient lakes. On the opposite end of the spectrum, this is rare, but it's neat to see the whole picture. We found places where the lakes clearly disappeared. So this is a slab of rock that's made out of that same mudstone that formed through lakes. So it was once soaking wet mud that hardened into rock. But unlike the other ones that sort of hardened underground over time, this one hardened at the surface. Something happened where the lake shrunk, maybe, or it got warmer for a few days or a few years, and the top layer of mud on this particular slab cracked, just the same way you'd find mud cracks in a drying pond or something like that. So it was really neat to be able to see these cracks, measure all of them, compare all their angles to mud cracks on Earth, and figure out that these mud cracks probably formed in a single day on Mars. So it's kind of cool to think. What we're seeing here, one day there was a lake, the lake receded for whatever reason, and in one day the mud cracked, and then it got buried, kind of like, the mosquitoes in Jurassic Park. If the right conditions happen, you can just bury it quickly and you preserve it, and 3 billion years later, we can study it. This shows some cracks in the ground that are filled with these white minerals. And this is also a pretty common thing you could find on Earth, where the rock that forms most of what you see here, in this case the lake sediments, was buried underground, hardened, then cracked, and then groundwater circulated through those rocks, and the groundwater had a bunch of chemicals dissolved in it that then precipitated out on the walls of the cracks and filled them with minerals. And this is calcium sulfate, gypsum or other types of calcium sulfate form these ridges, which basically are just the minerals that formed in ancient cracks. And now as the whole rock is eroding, the crack forming thing is kind of sticking out of the surface. So what's neat about this is it tells us that not only were lakes there for a long, long time, we think millions or tens of millions of years to get the 1,000 feet of lake deposits, but after the lakes were long gone and that mud hardened into rock and fractured underground, then groundwater was still circulating through them, still maintaining a habitable environment for some, much longer period after that to allow all these minerals to form. So not only was Mars habitable for the lakes, but even a era after the lakes when there was groundwater. So, starting to wrap things up here, Mars was once wet. Was it warm? We think it probably was. We don't still have the smoking gun evidence for that, but when you start talking about lakes that survive for millions, tens of millions of years, you probably do need something like a full weather system that can evaporate water from a lake or an ocean somewhere, and then have clouds in the atmosphere that bring it down and precipitate and recharge the streams that kept the lakes going for millions and tens of millions. Just your errant volcano going off won't provide the continuity that we see as the So we really do think the ancient climate was notably different and sustained in that different. So those are the answers. We think. I want to end, a couple more things. This picture came down today. If any of you were following the mission, you know why already it's very important. But if you're not, I'll tell you. So we had a really disappointing event about a year ago where our drill stopped working, it's pretty devastating when you're so emotionally connected to the mission like a lot of us are, because as you come to learn, the mission is really built around the ability to drill and analyze drilled samples in those laboratories. So the drill stopped working about a year ago. It just kind of became unreliable. It didn't actually stop working. And so we spent about 6 months trying to resuscitate it, trying to figure out if we could write different software for it. Do anything we could. Do it this way, do it that way, whatever it would like. We tried it, and we couldn't really get anywhere. And so then we spent now about 8 months after that initial 6 months trying to figure out, and when I say we, I mean the engineers. Again, nothing to do with this. I'm just the end user. The engineers at JPL spent about 8 months figuring out if they could redesign the entire way we drill to avoid the use of that broken part, which is really remarkable. So I'll show a little video, a 3-minute video that summarizes this, but the main motor that moves the drill up and down stopped working. And yet the engineers were able to find a way to, 100 million miles away, test on Earth using our backup test rover on Earth that we have at JPL, invent a whole new way of drilling that was safe and reliable to use on Mars, and then actually commanded to try this first drill. We haven't hit the home run yet, in the sense that we've drilled a small hole, and we still need to drill a deeper hole to be able to get enough material to deliver to the instruments, and this one didn't quite do that. But still, until yesterday, we had been a whole year without drilling on Mars. And so, yeah. Yeah, thank you. Here's that story.
Since Curiosity landed on Mars in 2012, it's used its drill to acquire samples from Martian rocks 15 times. But a little over a year ago, in December of 2016, Curiosity's drill started giving it problems. The drill's feed mechanism, which is responsible for moving Curiosity's drill bit into and out of rocks, didn't move when commanded. When Curiosity drills into a rock the way it was designed to, the drill's 2 stabilizer posts touch the rock first to steady the arm while the drill's feed mechanism moves the bit forward into the rock. Without the feed mechanism working, we can't drill that way. To solve this problem, we do what we always do. We worked it out in the test bed using Curiosity's twin on Earth. Our team of engineers and scientists have been working for months to figure out a way to collect and deliver rock samples without using the feed mechanism. Here's what we came up with. Using our new technique called feed extended drilling, the stabilizers are not used. The bit is now in a forward position extended past the stabilizers. Moving the drill straight into a rock and retracting safely without the stabilizers is challenging. We move the arm instead of the feed mechanism to place the bit onto the rock and press it forward as it drills. After making contact, we apply a light preload and drill a shallow pilot hole. We use a force sensor in the robotic arm to give Curiosity a sense of touch. This lets Curiosity adjust its arm motion and avoid getting stuck while drilling, kind of like you might adjust your arm while drilling into a wall at home. After drilling, we use a similar technique to retract from the hole without getting stuck. We recently tried this method using Curiosity on Mars, and here's how it turned out. This picture shows the first hole drilled on Mars ever with this new drilling technique. Even though we can't see the hole in this image, we know we drilled about 1 centimeter deep. The hole itself is buried under the powder generated during drilling. This is a good sign for the new drilling method. Next, we have to drill a deeper hole to collect samples and demonstrate our new techniques for delivering the samples to Curiosity's 2 onboard labs. That will come in the days ahead.
Yeah, that picture and that video literally is on the website about 3 hours ago. Glad I was in time for this lecture. So I think the last 2 pictures here before we end. This is one we took from our position now 1,000 feet high on the mountain, and we could, for the first time, we sort of turned a corner, got above a little blockage, and we're able to see all the way back to the landing site for the first time. So we landed here, and then we drove over here, made those discoveries in Yellowknife Bay, and then continued on. And this mountain range here is the far side of the crater. That's like 30 miles away from where we are on the central mountain. So we're looking across this 30-mile crater floor, and here's the mountain. So my final thing here is just to give you one slide of what's coming. Curiosity played an important role in the Mars program by understanding the habitability of Mars, and it was a habitable planet. The evidence now is really strong that we've determined that 3 to 4 billion years ago, Mars could have supported life. The question is, did life ever arise? And that's exciting that we can ask that now, because Curiosity could have had a very different answer. So now it's up to future missions to go look for actual evidence that life was able to use that habitable environment. And so the 2020 rover mission, which launches in 2020, is built on the same platform as Curiosity. It carries a payload that is designed to detect ancient signs of life. As we talked about, it's very challenging. So the instruments that we're bringing with the rover may or may not succeed in that. But what this rover also does is collect the samples that it drills, puts them in little vials that are sealed on Mars, and puts them in a canister so that one day a future mission can bring that canister of samples back to Earth, and we can use all the very best laboratories on Earth to understand if any of those rock samples contain evidence of life. So this is not only a really neat mission as the next step in understanding life on Mars, it's the first step in returning samples from Mars to Earth. Thank you very much. Okay, so the first question, do we find about the ancient atmosphere? Yes, I could talk for like 5 hours about everything we found, which is very frustrating because I want to tell you everything. But we have this whole other experiment we could do with one of our laboratories to suck in Mars air and understand what it's made out of. And one of the things you can do is look at the composition of the air today, specifically what's called the isotopic composition of the air. Molecules have light versions and heavy versions, and you can measure how many light versions and heavy versions there are. And what that tells you is that if Mars' atmosphere was lost over time, like we think it has been, you end up retaining a lot of the heavy ones because the light ones escape. So Mars' atmosphere has a lot of the heavy versions of different molecules, whether it's carbon dioxide, water, and that fits with this long-standing theory that the reason Mars went from wet to dry is because a big percentage of the atmosphere has been lost to space. So that's one of the things we were able to find out. And will 2020 have labs like Viking? Not quite the same ones. One of the things that Viking did in 1976-77 was to attempt to feed microbes in the soil and see if the metabolic products came on, sort of actively look for life living. That's not the kind of thing that 2020 does. It's more looking for what's called bio